This is pretty, what did we plan? Okay.
Oh, yeah. Are you okay with it?
Yeah, it's fine.
You're okay, yeah.
Sorry,
You should only let people grab their food and then we'll get started in a couple.
No, that's fine.
This. Or is it going to? Yeah. May have to.
Everybody.
Yeah.
You're applying for the job this new, yes.
Yeah. Today I asked for my first appointment.
Nice.
So it's officially started.
Good, good.
Yeah.
Okay.
Yeah.
Sorry. I'm glad it's not, but yeah, it feels good.
Why were you there? This has building?
Just-
All right, I think we're gonna get started. Welcome everyone to the AstroAI launch talk. Today it is my pleasure to introduce Christian Jespersen. Christian is doing his PhD in Princeton under Peter Melchior and also working with David Spergel at CCA. He has a broad range of interests on applications of machine learning to astrophysics. Lately, mostly extragalactic, but also dealing with gamma rays and diffuse interstellar bands and other things. So feel free to
Once upon a time, exoplanets. Did once, and then I decided I was never going to do that again.
Right.
Yeah.
And today is going to be telling us about graph neural networks and the applications for modeling of galaxies and how that relates to cosmological simulations, I'm guessing. So, or maybe not, but Christian, thank you very much. The floor is yours.
Sure. So thank you for the introduction, Robert. And yeah, so despite having worked briefly in exoplanets, I today mainly care about galaxies. That can be understood very broadly. Again, I might care about dust in galaxies, I might care about stars, I might care about galaxies as global systems, as cosmological traces, but it really is all about galaxies. That's because galaxies both are big and bright and beautiful and diverse, and we really want to know how they got to be that way. That means that we want to ask questions like, what are the building blocks of galaxies? What are the tools that we can use to bring those building blocks together over time? Like, what are the forces that we can use to bring those things together over time? And how exactly are they brought together over time? In short, what we want is something like an IKEA manual, where it's clearly outlined that when you go down to IKEA and you get your galaxy, these are the things you'll get in your box. These are the tools you'll use to put those things together. And this is the way that you're going to put everything together. But of course, again, not in normal IKEA, but for galaxies. If you ask, I'm Scandinavian, by the way, so I'm very entitled to make this joke. If you ask somebody about like what is the IKEA, what does the IKEA manual of galaxies look like? The answer you're likely to get is something like, well, it's something where you'll get a bunch of stars in the box, you might get a dark matter halo. You'll definitely have to use some gravity to put it all together. If you're lucky, there might be some gas, some dust, but that typically is where the story ends. But you will immediately notice that there is a stark difference between this kind of IKEA manual and the one that I had before, which is essentially that it's missing all of the assembly bits. We know that galaxy assembly is really important because, well, we can simulate it. And when we simulate big structure formation simulations, so this is just a big n-body simulation, we know that individual halos, and therefore the galaxies that live inside those halos, don't just form nice and neatly and evolve on their own sectionally. They ram into each other and merge, which fundamentally changes both the halo and galaxies. The way that we tend to incorporate this merger history, we tend to track this merger history is in something called a merger tree, something like this. The way you get a merger tree is just by running a simulation like the one I showed you before, and you'll just stop it at a given time, you'll identify all the halos, and then you'll run it a little bit forward again, take another snapshot of the simulation, identify all the halos, and you just keep track of, well, what merged with what, and what continued on just being its own thing. Of course, what we really care about is not dark matter halo merger trees. These are mostly dominated by dark matter because this is, things that merge is something that's mostly dominated by gravity. And after all, dark matter is where most of the gravity comes from. So there's mostly a statement about the dark matter. What we really care about is galaxies. We want a way to also get galaxy properties out in the end. And in general, there are two ways we can do that. The first way is by using something called a semi-analytic model, where we take the dark matter halo merger tree from a simulation as a fixed thing, and then we evolve a set of coupled stochastic differential equations on top of the merger tree in order to produce our galaxies in the end. The other way is to just simulate everything all at once in a kind of more traditional, I don't know, maybe not more traditional, but in a full hydrodynamic simulation where we just co-evolve everything so we get the galaxy properties and the merger tree out at the same time. Both of these form really, really complicated relationships between halos and galaxies. And because it is such a complex thing, a lot of people have, over the last decade, tried to use machine learning to go from halos at a given time to the galaxy, to the properties of the galaxy residing in that halo. This has, in general, not been something that's been super successful. And a big reason for that people often blame for the lack of success is the fact that they don't know how to incorporate the assembly history of this galaxy halo pair. That's an understandable challenge, because if you look at something like this merger tree here, a natural question to ask yourself is, well, how would I put this into an algorithm? When we make algorithms, we like for our things to be either rows and columns, matrices, tensors, and this is neither something that can be expressed on nice rows and columns or a matrix or anything else. So it really doesn't fit with all of the traditional algorithms we tend to write. The way you can get around this is by instead of viewing this as what is called a graph. When I say a graph, I of course don't mean a figure, like a graphical figure. What I mean is a topological graph. That is defined as just any set of nodes or points that can have a set of features that are then connected to other nodes with a set of edges that can also have some set of features, where the edges typically in code are these two nodes related in some way. This is a very, very vague definition of a data type, but because it is so vague, it allows us to work with a very, very wide range of new kinds of data that we weren't able to work with before. It also has the advantage that while something like a matrix makes an implicit assumption about the geometry of the data we're working with, this does not. That means that we don't have to make an implicit assumption about geometry, and we can later on make more explicit definitions of what kind of geometry we think our system has, or just leave it out completely if we actually don't know what kind of geometry our system has. This is something that is incredibly helpful for physics, because geometry has always been one of the cornerstones for constraining our models of physical systems. And of course, you can put up long quotes of like, yeah, geometry is super important. But I think I was never as convinced as once when I was visiting the Perimeter Institute in Canada, which just has a big plaque next to the door that says something very simple: let no one interested in geometry enter here. It is a super interesting, and also this, by the way, comes from Euclid's temple. The version in Greek comes from Euclid's temple in 400 BC in Greece. This has always been important for doing science. So we have these two really, really important parts of working with graphs, which is both that they're very adaptable, but also that they allow us to think more freely and geometrically, which is really important for physics. In general, this means that a lot of systems that we encounter in real life are easier to express as graphs than anything else. The classic poster child of this is molecules, because of course you can. It's almost embarrassingly easy to see why this is expressible neatly as a graph. A molecule is a collection of points with properties, in this case, atoms with charges and atomic numbers that are connected to each other by edges, or by molecular bonds that you can encode as edges. They can also have some set of features like the interatomic distance and the strength of the bond, all that kind of stuff. Of course, if we want to move closer to astrophysics, you can look at something like large-scale structure. You go and look at a bunch of galaxies or halos, and you just say, actually, I think that galaxies and halos mostly interact with other things that are close by. You can make up some edges and say, I'm just going to take all these things and then connect them to everything that's close by, and then I'll have myself a cosmic graph. Both of the graphs that I've shown so far encode some kind of spatial relationship, but you don't have to limit yourself to spatial relationships. You can, of course, also do it with something like a merger tree, in which case you're encoding a causal or temporal relationship. So graphs are super versatile, and they allow you to think much more freely about the data you're working with. Because this is supposed to be a bit of an introduction to graph neural networks as well, I wanted to zoom out a little bit and go through some definitions, so that in case you have some problems, and I think you probably do, that are suited for using graph neural networks, you'll be probably prepared to do so. So just to zoom out. So what makes up a graph again? So we have the nodes, and the node features. Again, usually you'll just see the node features stacked in something like a feature matrix that's down here. I've been told that people in the back probably can't see what's written down here, so Yes, I see. Yes. And you usually see this written instead of in matrix notation. You usually see this written in set notation because graph theory really came from set theory. And I can also tell that this is on the wrong side of the screen. Anyway, I don't think you'll be able to sell this. Anyway, same thing goes for the edges and the edge features. They'll also often be written in this set notation that you guys can't see. But because the edges are usually used to encode the features, when we talk about the edges, we usually talk about the edge features. People will often also introduce a separate but related concept, which is called the adjacency matrix. The adjacency matrix is something quite simple. It is just a binary matrix that encodes whether or not node I in a given graph is connected to node J. So, the rows matrix is the sending node, and the columns are the receiving nodes. So here, when you have a 1 on row 1 and column 4, it just means that node 1 is connected to node 4 here, and it's not connected to anything else. So that's why there is 0 all around here. One of the things that you'll notice about these matrices here is that they have two properties that they don't necessarily need to have. One is that they're symmetric. When they're symmetric, we call the graphs undirected. That just means, right, that like every time that you can go from node 1 to node 4, every time you can go from node I to node J, you can also go the other way from node J to node I. That doesn't have to be the case, in which case you call the graph directed. For example, for our merger trees, when you're embedding some sort of causal structure into a graph, there is a preferred direction on the graph because you have a direction of time. You cannot have information go back in time. It has to go forwards. And so there you have a directed graph. Whereas in a spatial structure, well, interaction can go both ways. And so there you have to have an undirected graph. Another thing that you'll notice is that this doesn't have any ones on the diagonal here. When there are ones, we call that having self loops for natural reasons. It just means that if I start with node 1 and I have a 1 on the 1, position, I go from node 1 and back to node 1. What the adjacency matrix can also be seen as is a instruction on how to walk on this graph here. Like if I start in a specific state, so let's say I start in the vector state where I start, let's say in node 1 here, so I have a state that says 1, 0, 0, 0, and I act on that vector with my adjacency matrix. I see that I'll walk to node 4 and node 2. So in that sense, it gives me a sense of what is the neighborhood, the local neighborhood of each node. This might seem simple, but it's actually really, really useful for physics to frame things in terms of neighborhoods, because most of physics is local. Almost always we have some set of objects that interact with some set of objects, but they don't really care about everything else that's going on in the universe. And it's very, very useful to be able to embed this directly into your data, that you can interact with these things here, but not these other things here. They're all nth order events. The last thing that you'll see come up sometimes in definitions of graphs is a set of global features. In cosmology, this might be something like, well, I have this large-scale structured graph, and I might want to just have a feature vector that says I have this omega m and sigma 8, and that's what gave rise to this cosmic graph here. So again, just to round up, you'll have a definition of graphs often as G as V. This is the nodes, vertices, the edges, and then this U global vector, which is an optional thing. So you'll sometimes see this left out. And then you'll often also see this definition of the adjacency matrix, something separate, even though the same information is encoded in the edges. Okay, so now that we have our graphs, let's go talk a little bit about how graph neural networks work. And here, I will generally talk about this in terms of how we tend to communicate as people. Because of course, social networks are also graphs, and the way that graph neural networks were first formulated were to a large part identified in the way that we share information between each other. So in general, graph neural networks work with something called message passing, which means that in order to update the latent state of a given node, that node will take in information from its neighborhood, aggregate that information, so do some kind of summing over the information it receives from its neighboring nodes, and then combine with its current state, have some kind of update function. There are in general 3 kinds of layers that you can use for this. Some people call them all message passing layers for obvious reasons, right? This structure reminds one a lot of just passing messages. And so some people will call them all message passing layers. I much more prefer, just for the sake of clarity, the framework where we split them up into 3 distinct categories. They're all special cases of one another. The attentional layer here is a special case of the message passing layer, and the convolutional layer is a special case of the attentional layer. So in that way you could unite them all under one framework, but I would say that's just graph neural networks.
Sorry, could you explain exactly what's happening inside the parentheses here? What's the operation?
I will do that in just a second.
Thank
It's a very good question. Sorry, we'll do that in just a second.
you. Thanks.
Because the attentional layer is a special case of the message passing layer, and convolutional a special case of the attentional layer, that of course means that in general you get less complexity as you move to this side of the board, but you also get faster training times and quicker inference. So if your problem does fit one of these simple layers, you should pick that layer, even though this one here is more expressive. But just to go through how each layer works, as requested by Rafa, for the convolutional layer, let's say that I want to update my opinion about something semi-controversial, like whether or not pineapple belongs on pizza. I might have an opinion myself. That's my current state here. But in order to, I haven't eaten a lot of pineapple on pizza, so in order to figure out whether or not this actually is a wise thing to do, I might want to go and add people that I know, some of the people that I've met here. And they will then tell me what they think. They have their opinions, and they have a little message function that they can learn. They can learn how to express their opinion, and then they will express their opinion to me. I will aggregate over all the messages that I get, and I will take the aggregate of the messages and my own opinion, and I will update my own opinion. This is essentially equivalent to just everybody shouting their opinion out loud. So this is kind of the stupidest possible thing you could do in order to get some consensus on what is the best way forward here. You could take it one step further and go to the attentional layer, where now you still have people just saying their opinions as they are, but they are now allowed to weight them based on what they know about me. That's my XU, so they know whether or not I like pineapple on pizza. So maybe if Rafa likes pineapple on pizza, he knows that I don't like it. He might choose to weight. I might choose to weight his opinion differently because obviously he is crazy. There's also this edge feature here that could encode like how close are we? Are we in general in a position where I'll be very swayed by Rafa's opinion or not? But this has to be expressible as a scalar. That's why the intentional part of this layer comes from. You get the original opinion just as before, but I get to weight it up and down by this much more complicated function that depends not just on Rafa's opinion, but also on my opinion and the relationship between me and Rafa. The last kind of layer, the message passing layer, is where the thing that Rafa says actually depends on all these three things. So Rafa, in order to not offend me because he knows my opinion, might decide to change what he actually says. This is not just scaling up and down the thing that he would otherwise say. This is completely changing what he would say. And he can also modulate it depending on how well he knows me and how well we know each other. So here, just want to stop. Any questions on these three layers here?
When you say how close you are, is there any physical distance between nodes that will tell me how close we are? Or is this, for example, how far away you are in the neighborhood? Like what exactly when you have these different nodes makes the
So
node
when you have an edge feature, then we have to have a direct edge between us. But it might be something that says like we've known each other for 5 days now, right? That's the length of time we've known each other. And that could be an edge feature, right? So this is not how far away he is in the graph. It could just be something like, in order for this to exist, he has to be part of my neighborhood to begin with, and then it could be something that encodes, how well do we know each other in this case. If you're doing something else, like for example, learning about molecules, what you could have here is something like, what is the spatial distance between two things, right? So that you learn how to change your message based on the distance between two objects. Might you also?
I did this more of a general question, I guess.
Yeah, sure.
I know I haven't heard the message passing layer yet. I know an attention layer, putting transformers, and the CNN is convolutional layers. So I was wondering if anyone has used message passing layers in a general neural network framework that you know about.
Not
the graph networks.
Not really. And it is the main reason for why people haven't used them outside of kind of the graph literature is that often these just take much longer to train. Simply, they're just much more computationally expensive, and they don't fit into a lot of really important physics things. So if you look behind what like AlphaFold V2 is running, there's a lot of this running AlphaFold V2. But if you look at, for example, text, you don't actually have a lot of stuff where you get this kind of bimodal or bidirectional interaction, there you get much more kind of straight up normal attentional things.
Okay.
It's just much more expensive to train, and therefore it is much more expressive, but it's also much more expensive to train. In general, I will say though that if you're working with graph, when you're working with physics, I tend to prefer these over attentional layers, just because attentional layers are also very limited in what they're allowed to express, because you are just doing a scalar kind of way up and down of whatever thing you have.
Okay.
Yeah. Sure. Anybody else? I'm happy to take any questions here.
I do have another.
Yeah, sure.
So do you give an example on either molecular biology or galaxies where this change your message situation can happen in the message passing case? Like you said, this is like equivalent to me completely changing what I say because I know your opinion.
Yeah.
What is the physical equivalent of that?
So the physical opinion of that is, let's say the interaction between three galaxies, right? You have one galaxy that has like intermediate mass, one galaxy that has a very large mass, and one galaxy that has a very small mass. Let's say the medium mass galaxy is sitting in the middle. It will have a very different message to send it to the galaxy that's much smaller than it, than the galaxy that's much larger than itself. Does that make sense?
Yeah.
Right? The way that I interact with as an intermediate sized galaxy, the way that I interact with galaxies that are much bigger than myself is just fundamentally different than the way that I interact with galaxies that are smaller than myself. Does that make sense?
I don't know. I guess it does from some perspective.
I can maybe try to come up with another metaphor afterwards, but I'll leave it at that for the time being.
Yeah.
This is what we see when we try to do graph learning on galaxies, is that you do actually require these message passing layers. And if you only have like the scaling up and down of the same message, you're really missing out on all that stuff, because there is a complex interaction between, if you are one type of galaxy and you're interacting with galaxy type 1 into galaxy type 2, that does change the way that you're interacting. Yeah. Please, yeah, you first.
Do you give me like an idea for the memory constraints of the graph, and if it has to like nodes or edges to get all fit on
Depends on the amount of nodes and edges you have, but yes, they are quite memory intensive compared to something like again, this goes back to Mike's question. They are quite memory and compute intensive compared to something like just a normal transformer, which is why, again, you can think of transformers as just like graph attentional networks, and people have written papers being like, you guys are all just doing graph networks, why aren't you saying it? But there is a lot of optimization that you can do if you know that this is the only way that you want your interactions to look. Then you can do a lot more optimization. That's why transformers. I'm not recommending you should do graph attentional networks for big language models.
But for the merger trees, like the entire tree fits into your graph.
I'll actually talk a little bit about this in a little bit. So when I get back to my science bit, so wait a little bit. You also had a question? Okay, similar. Okay, well then let's get on. So what can we do now that we have our graph neural network layers? Well, in general, there are three kinds of tasks that we can do. We can either do node level tasks. We can do graph level tasks, or we can do link level tasks. So something where we're doing something, we're trying to figure out something about the edges, something about the nodes, or something about the entire graph. In general, all of this picture here is this classification. You can of course do both regression and classification for each of these types of tasks, and that covers pretty much everything you want to know about a physical system. One of the things that is worth noting about graph neural networks is while they're not optimized for language, they are optimized for doing physics. And it's worth thinking a little bit about why they're so good for doing physics. The first thing is something that I've already touched on, and it's the adaptability. In general, these things can work with data that nobody else can work with, and that makes them really useful, just because you can always cast those data as graphs, and then you can put them into your graph neural networks. The second thing is this question of geometry. Because you make an implicit assumption about the geometry of your system when you're casting your data as graph, that means that you can either leave out any symmetries that you don't want, right? For example, if you use a convolutional neural network or something like a grid, you're making an implicit assumption that not only is the data existing in a regular Euclidean space, your signal also has to be a regular Euclidean signal. And very few things in physics actually are regular Euclidean things. This is most of what we get in computer science, but in physics, it's actually pretty rare that we find something that's that simple. Or, of course, if you do actually have some different symmetry groups that you want your graph neural to obey, you can usually bake that in. So if I know that my the signal that I'm looking for has some kind of translational invariance, some kind of rotational equivariance, some higher order, like some more complicated group action that it has to obey, I can always bake that into my graph neural network, which is not a freedom I have in most other cases. The next thing is that they are very nicely physical. Graph neural networks were first proposed and designed by physicists for doing physics. That means that the way that they work fits very nicely with our physical intuition. Like this way of saying, hey, well, and a good way of seeing that is if I ask anybody here to draw me something like a free body diagram, something that everybody has done in undergraduate physics, or even something like a Feynman diagram, what you will draw eventually will end up looking like a graph and a graph neural network acting on that graph. That means that they're very intuitive to use for us physicists, which also makes them much easier for doing interpretability later on. It also helps a lot that they have this inherent kind of zero order, first order interactions where we say, okay, what is my state right now? And then what is the interaction I have with my environment? It's a very easy way of thinking about doing physics, and pretty much the way that you would write up a physical system, kind of the dynamics of a physical system, if you had to in almost all cases. Related to that is the question of inductive biases. So do people know what I mean when I say an inductive bias in general? Yeah, I see free nodding heads, so I'll go a little bit more into it. When I say an inductive bias, I mean biasing our learning algorithm to learning something that I already know to be true about the system. And when you as a scientist, you encounter a problem for the first time, it's quite rare. You don't know anything about the kind of solution that you're looking for. Most of the time you'll have some idea, because you're a physicist, you have a lot of training behind you, you have some idea of how the solution you're looking for is supposed to be. This is related to the question about geometry. You can bake in geometry to know the geometry of the system, but often you can go even further, and just because you have such a flexible framework, you can bake in things that you already know about the system, and that tends to help with finding the right solutions. As an example of this, I wanted just to show something completely unrelated to what I'm doing now. That's something I worked on 5 years ago, which is the ice cube neutrino detector at the South Pole. So this is both a really cool experiment, because it's about 10,000 light detectors drilled in long strings into about a square kilometer of ice on the South Pole. They're arranged in this very weird structure here. And what they're supposed to do is just to sit around and wait for neutrinos to go through the ice, interact with the ice, and then produce Cherenkov radiation, so that all these different detectors will light up and you get these signals. And then the name of the game is to reconstruct where did this thing come from, what kind of particle is it, and how much energy did it carry. But again, if we go back and look at the structure of this, you can see how this might be a modeller's nightmare. Look at the mess here. There's an irregular hexagon with a corner cut out. It like could not be worse for doing any kind of computation or modeling. And to make matters even worse, they're like, okay, in order to heighten our sensitivities to low energies, we also need to put this other little irregular hexagon rotated compared to the first hexagon with a different detector spacing than the rest in the middle. And that meant that this is just a nightmare for anybody who wants to do any kind of statistical learning. Of course, that didn't stop people from trying. So people still tried to get this on a nice regular grid, and then to use convolutional neural networks on this when it was first built in 2019. So it was the state of the art at the time. But that doesn't really work. First of all, because this thing just isn't regular. But again, because when you're using a convolutional neural network, you're telling your algorithm to look for things that can be expressed in nice Euclidean regular space. And the big problem you get here is that because there is this different density of detectors in the middle, signals that end up hitting here just look fundamentally different from signals that end up hitting here. They just look different. So you don't have this translational symmetry that is inherent, that you cannot escape from when you're using a convolutional neural network. So there's a lot of motivation for why you should adopt a graph neural network here, both because you can actually get your data to neatly work with this, with these different, again, you just have a bunch of different DOMs. They're called DOMs, the detectors, and you can just connect them depending on your signal. So what you will usually get is that you'll get a signal that comes in, and you'll have all these different DOMs that light up. You will have to make up a graph structure, because of course the graph structure isn't something that is given a priori. You don't know which detectors to connect to everything else. But again, this is where you can come in as somebody who knows physics, and you can say, well, I can probably make a good scheme for making the edges of my graph. The way we ended up doing it is to say, well, every one of these detectors that goes off and is within one light travel time between one trigger and another trigger gets connected to one another. This comes from a very simple physical principle, which is that signals cannot travel faster than light. And so this gave us our graph structure, and it actually ended up being really, really good and working really well. So right now we have 4 GPUs at the South Pole that are running all of the neutrino detections in IceCube, which I think is pretty cool. So just to sum up, GNNs are really good for physics, unreasonably efficient. That's because they marry physical intuition, the ability to work with a lot of real data, with group theory and geometrical constraints, which are really, really important in physics in general. Okay, any questions here before I go on? Okay, great. So now back to my IKEA manual. So again, the IKEA manual for Galaxies really lies in the merger tree. But to the question that was asked before, this is actually not how merger trees look like when they come out of simulation. Merger trees, when they come out of simulation, when you get handed them by a theorist, they look something like this. As you can see, there's a lot of stuff in here, but it's just Galaxies just evolving on their own. And I know, because I've learned about Galaxies, that when Galaxies are just evolving on their own, they're actually pretty easy to model. The hard part of modeling a galaxy is not when they're just on these like long, narrow tracks and they're just evolving on their own. The thing that's complicated to model, the thing I want my machine learning model to do, is figure out what happens when they merge. That's when things get complicated. And so again, I can put an inductive bias in my data, not in my algorithm union, but in my data by restructuring the graph. So I keep all the causal structure, all the causal structure is the same, but I'm just going to condense these long branches here so that I'm only keeping the halo when it's first identified and right before it merges and of course after it merges. And that cuts down on the number of nodes I have in each graph by somewhere between factor of 10 of 100. And it also teaches again, carries this implicit bias that the thing that you need to focus on when learning about galaxy evolution is the mergers. It's not all the other stuff, that's simple. Focus on the mergers. Nice. So now I have my merger tree, which I can think of a graph. That means I can use my graph neural network. And when we train a graph neural network to emulate a semi-analytic model, we can of course make a new architecture, and that gives us the right to make a name and a logo. And what all of our effort gives us is, of course, vastly improved predictions of stuff like stellar masses. Here I'm comparing to a kind of traditional non-parametric method called abundance matching. And this plot here is just this classic plot that I'm sure most of you here have seen many times before, where on the x-axis I'm showing you something that came out of the simulation that I'm trying to match. And on the y-axis, I'm showing you the prediction of whatever method it is that I'm showing. Of course, the name of the game here is to see how close I can be to this one-to-one line here. And with the summary statistic that encodes how close I am, the typical is the scatter or the typical error, which for abundance matching, when trying to reconstruct stellar masses, is about 0.3 dex. And for my GNN, it's about 0.07 dex. So we get about what at face value looks like a 4 times improvement. That's pretty nice. It actually is a little bit more impressive than it looks like at first sight, because if you remember that semi-analytic models are not just normal ordinary differential equations, they're stochastic differential equations. There actually is a little bit of noise in the simulation itself, which means that if I take SM and I change the random seed and I run it again, I will actually get a slightly different result out. That noise is something that you cannot model with an algorithm because by its very nature it's stochastic, so you cannot model it. And so there is a flaw to the best possible performance I could get with an algorithm. It's not 0. In this case, it's actually 0.05 dex. And so 0.07 is pretty close to 0.05 dex. So I'm doing about as well as I possibly can. Of course, you might object to this and saying that, well, abundance matching is like it's a one parameter model that has been used for 25 years. Maybe it's not the fairest comparison to your GNN. The thing you really should compare to is an MLP or a random forest on the full set of features of the redshift 0 halo. That's agree. That is the appropriate comparison, and this is how they compare. So here you can see that the scatter is about 0.13 dex, so still about twice as bad, 2 times worse than the GNN itself. So this lets us have some confidence that our GNN is actually performing really well. Another thing we can look at is just typical scaling relationships, like the relationship between halo mass and stellar mass as they come out from our simulation and from our GNN. And here it is for the simulation, and here it is from the GNN. It's pretty hard to tell the difference between the two. Not only do we get kind of the general trend right, one of the things that we were very excited about when we saw this is that we get the outliers right. And of course, it is something that's worth thinking a little bit more about, because in general, GNNs, while they are fantastic, are still just statistical learning machines. And that means that by their very nature, they tend to deprioritize outliers. And so we were actually a little surprised to see that these 3 points here that are about 3 orders of magnitude away from the mean relationship at their halo mass still are dead on. That's pretty exciting.
You're missing a couple on below, right?
Yeah, so this, yeah, well, you're missing a couple down here. What actually ends up happening here is that we're using a full Gaussian likelihood where you're predicting both the uncertainty and the essential value. And what happens down here is essentially the argument says, I would much rather just take the penalty of assigning a huge uncertainty to these and then not push them as far down. And
I was
so
thinking more of the ones like down there, like in the middle, 11.3 or something.
yeah, this one here is still there, but yeah.
Okay.
But yeah,
I'm
it's
trying
just-
to be overly critical of them all. I'm just saying, like,
No.
do you have a preference to get outliers that are above the correlation?
In general, because in general you do, and that's because the things that tend to be above the correlation tend to have larger murder trees, and therefore we have more information to base that prediction off. Again, of course, when you're predicting both a central value and an uncertainty, you always have to, the algorithm always has the option of just assigning a giant, of course, with a penalty, but assigning a giant uncertainty and then putting it closer to the mean relationship. And that's usually what happens down here, because these murder trees tend to be a little shorter, so there isn't as much information to condition on. But that's mainly a question of the resolution of the simulation that we're training on. If I had a high resolution simulation, there was as much information, then you'd be able to push this down below just as much as you'd be able to push it up above. Okay, cool. But of course, this means that we have a very, very nice algorithm, and that means we can start asking questions of the algorithm that we can't ask of the simulation. We can ask a question like, what part of a galaxy's history is most determining for its properties? Are galaxy properties determined in the early universe? Are they determined in the late universe? What's actually most important? And the way we're going to do this is by simply taking the murder tree, and then we're going to just trim it from early times and just say, we'll take the trim murder tree and just run it through the algorithm and see what kind of precision we get out in the end. And the results end up looking like this, where over here, we're using the full murder tree, and then here we're only using half, and then up until here, we're only using the properties of the final halo. And the interesting thing you'll see here is that essentially the first half of the merger history doesn't really matter. Whereas on the other hand, the last percent, going from having access just to 1% to 0% of the merger history, does have a statistically significant difference. This kind of makes sense. You know, galaxies mostly remember the things that didn't happen all too far back in the past. But it's still a good check to still a fun thing to be able to investigate. Of course, all the things I've shown you so far have been for the semi-analytic models, and it's kind of a given that this is going to work with a semi-analytic model. After all semi-analytic models are based on merger trees themselves. So you could of course ask, well, does this work as well with a full hybrid simulation? Like their galaxies might be less coupled to their merger histories. So we can of course try this out. And what we see now is that we get a more modest improvement. What you're seeing here in these dashed unfilled contours is the performance of just using an MLP on a redshift 0 set of halo features, whereas in the filled colored contours, you see the performance using a GNN. And so here we're going from a typical error of 0.19 dex on the halo only to 0.14 dex when using the GNN. So the question is then, is it because merger histories actually are less predictive of galaxy properties in a full hybrid simulation? And the answer is no, that's actually not what's happening. Because the main thing that's changing when you're going from the SAM to TNG, and this is something it's worth paying attention to, but if you're ever using TNG to provide you with good labels, is that the chaotic limit in TNG is just that much higher. The chaotic limit of TNG is at 0.12 dex. So if I take TNG and I just the effects of chaos change the stellar mass of galaxies by a typical 0.12 dex. The way you do this in TNG is not by just changing the randomity and then running things again. The way you do this is by exploiting something called the butterfly effect, which is something that was pioneered by Shai Ganal at CCA. The way you do this is by taking TNG and you run it forward to redshift 5, where you start to be able to identify proto-galaxies. Then you split, you take your little TNG box and you split it up into 2 shadow simulations, where in one of the 2 shadow simulations, you induce a number of artificial rounding errors. So you take all the different particles in your galaxy and you induce artificial rounding errors. Rounding errors are things that happen all the time anyway, so these are things that your galaxy should be robust to. Right? This is the smallest possible disturbance I can make to my galaxy. And then you just run it forward in time and you see what you get in the end. And oftentimes what you'll get are 2 galaxies that look very, very different. And again, you can take this as TNG's ability to reproduce itself. Generally not something it's able to do. That means that the labels that I'm training on and the labels I'm evaluating against are very, very noisy. So in general, you get the same answer from both, even though at first glance might look like there's less of a connection in TNG. But if you're doing it relative to the chaotic limit, you get the same answer. So when you want to build a galaxy, you have to read your manual, and your manual is the merger tree. Of course, in astronomy, we often don't have access to the merger tree because it is not something that is observable. So the question then quickly becomes, what do I do if I can't find my manual? And of course, for galaxies, you do the same thing that you do that you would do in real life, which is to go and ask your neighbors. In galaxy terms, this means to go and look at the environment of different galaxies. We know that observationally, different galaxies, the same galaxies in different environments just have different properties. Like galaxies in different environments just have different properties. And as I showed you before, you can very easily take the same framework that I just introduced with graph neural networks and use it on large-scale structure, because you can take any simulation or any set of observations and then just identify all galaxies or halos, and then connect them onto certain local length scale in order to make a graph. Notice though here, compared to the merger tree, here the graph structure isn't given a priori. There is no causal structure that I need to obey. There's no set length scale that I have to connect galaxies on. I'm pretty much free to pick any scale that I want, but of course this turns it into an interesting question. What is the best scale to connect galaxies on? Just to give some intuition for how this looks, as I pick different linking lengths, this is how my cosmic graph will look if I pick a linking length of 1 megaparsec. You see, most things are not connected. This is also for a sample with minimum halo mass 10⁵. This is how it looks like if I connect things on 2 megaparsec scales, and on 3 megaparsec scales, where you will see this classic cosmic graph structure really clearly come forward. Of course, an interesting question that I think is good for everybody here, so then maybe take 2 seconds and ponder, is whether or not you think my environment GNN is going to be better, worse, or have about the same performance as my merger tree GNN. Because this tells you a lot about whether or not you think the merger history or environments are most important for galaxies, or whether or not they are degenerate with each other. Okay, you don't have to answer, just keep the answer to yourself. I just wanted everybody to take a second and think. But let's take a look at some results from this. So here I'm first of all plotting the performance in just an MLP that just uses the redshift 0 halo features. And then here in the blue line is the performance of my merger tree GNN. So let's see how my performance evolves as I grow my environment to be larger and larger and larger. What we get is something that looks like this, where you see that as you grow what you consider to be your environment to include larger and larger scales, you get closer and closer to the performance of the merger tree GNN. You tend to asymptote towards this merger tree GNN. So there seems to be, first of all, no complementary information in the environment and the merger tree. They actually encode pretty much the same thing. We've also tried making versions of this GNN where we say, well, what if you actually take both the environment and the merger tree at the same time? And it never beats just the merger tree. So you really don't get any complementary information out of these 2 things. They're about the same, but together they also give about the same answer. One of the interesting features you'll see here is, of course, that this line here has one rate of improvement early on, and then it flattens out. It has a break length where it goes from one rate of improvement to another rate of improvement. And we were a little curious about this break length here. Like, I wonder if this has anything to do. I wonder if this would tell us why there is such a degeneracy between these 2 modalities. One of the hits to solving this puzzle that you can look at is if you, instead of taking a sample that has minimum halo mass of 10 to the 10, you go to a sample that has minimum halo mass of 10 to the 11, where the curve of improvement looks like this. So you can get this very characteristic sigmoid shape where you at first have one rate of improvement and then flattens out, you get another much shallower rate of improvement. And here the break length is about twice as high. So you wonder, okay, where's this coming from? And one of the things that we were wondering is, well, we're trying to emulate the semi-analytic model, which again has to be a function, by its very definition, is a function of the murder tree only with an environment GNN. So this has to be related to something in the murder tree. I wonder if it could be related to the extent of all progenitors at the first snapshot of the simulation, so at redshift 121, so in the beginning of the universe. And so we tried just computing the typical extent of halos in our data sets and plotting it alongside our break lengths here. And here in blue, you see these typical break scales here. And then you see in red, the typical extent of all progenitors at redshift infinity, effectively. And you see for the two samples here, they both line up. So it gives us a bit of a hint that this might have something to do with it. Of course, if you then go and tell this to a theorist, they'll be like, yes, I could have told you that. This is something called the turnaround radius, and we knew that like this was going to be the scale. Somewhat overconfidently tell you that we knew that it was going to be the scale that was going to be most important to consider environments on. So you actually wasted your time. We knew that already. But it's still something that's interesting to see. The turnaround radius, just for reference, is the radius, is the scale on which everything will eventually fall into that halo. It's not the scale on which everything has already fallen into the halo, but the scale on which everything will eventually fall into that halo. So this is kind of the simple explanation. Why exactly this then manifests itself in the present day environment is still a little unclear to me. So if anybody has any ideas on why this is happening, I would love to hear them. But of course, we're going to have to do our SAM TNG check, because all the things I just showed you are just using the semi-analytic models. We have to see, is this the same in TNG? When we try that, we find something similar. Here is this curve of improvement for TNG in purple. You see it also has this very characteristic shape, but it has one linear rate of improvement, and then it hits some break scale, and then it gets another but different rate of improvement. And it's also about 2.6 megaparsecs, just as the same as for the SAM. And so we get the same answers out of looking at the semi-analytic model and out of the hydro simulations. So we know this is a pretty robust conclusion. We don't know exactly what is making it occur. Okay, so just to sum up, GNNs are awesome physics. I will die in this hill. I love GNNs, and I will evangelize everybody until I die. They're fantastic physics. For accurate galaxy modeling, we in general need to go beyond single halos. We need to look at environments, and we need to look at murder trees. And when we look at both environments and murder trees, we get an improvement. But we tend to get the same improvements from looking at environments and murder trees, which tells us that these two are somehow degenerate in the way that they shape galaxies. It also provides a really interesting direction of future research, which is that you should be able to constrain murder histories quite accurately from looking at environments. This is something that nobody has ever tried doing before, of constraining the dark matter assembly histories of individual observed galaxies. What we're showing here is that given perfect data, admittedly, that should be possible. So it's a good question whether or not real observational uncertainties are going to destroy this. But again, in theory, this should be possible. And of course, I like to do GNN-related projects, and I've supervised a lot of GNN-related projects on top of doing a lot myself. And so if any of you have any projects that you feel like would be suitable for this, I'd be more than happy to talk to you. And I'm up in B412 until the end of tomorrow. And so come by and find me or shoot me an email on cj1223@princeton.edu. Oh, I actually have a final quote because I think it fits this so well, which is something from an astronomer at the University of Pittsburgh called Rachel Bazanson. I just figured I would share it because I love this quote. In astrophysics, everything is connected with everything is connected with everything. And I think this fits very nicely with this GNN approach.
I would have put additional quote between here and here, but yeah. All right, thank you so much. That was very interesting. Do we have questions for Chris? Yeah.
Yeah, so, not all murder trees are created equal, like, so this kind of goes to your environment question as well, like, have you seen how the GNNs perform if you isolate like BCG, murder trees or selections on like the color of the galaxies, right? So that you have like the red galaxies have and trained on red galaxies versus trained on like star formed galaxies and things like that.
Yes, so we have tried that, and it depends on exactly the feature you're talking about. In general, we actually don't find all too much of a difference between the different kinds of galaxies. Of course, if you're trying to regress and I think a lot of the things get a little obscured by the fact that there is different level of noise in these parameters for different kinds of galaxies. For example, one of the things that we found a little puzzling is that it seems to be easier to predict the star formation rates of old dead galaxies in these simulations from the environment than from star forming galaxies. I don't think that's because it actually is easier. I think that's because star forming galaxies in all of these simulations, star formation is the most stochastic component, so the thing that has very, very high noise. And these essentially have lower limits where they put the star formation rates and say, okay, you have a specific star formation rate of 10 to the minus 11 solar mass per year, and per solar mass, and that's kind of the minimum you can get to. Whereas the second you actually start having star formation in one of these simulations, it just fluctuates wildly for no other reason than the fact that you need to put some stochasticity in the simulation to make them work. So we do see some differences. I'm a little hesitant to really strongly point out exactly what's causing them, because I think some of it is just simulation physics.
Paolo and then Helen.
Okay. Hi, so you talked about combining the environment and also the merger history, like the merger tree. So these seem like different modalities of data, right? Like how do you deal with like multimodality in GNNs?
No, they're just two graphs. You have one kind of graphical network that acts on one part of one set of graphs and another one that acts on all the other graphs. You just concatenate the latent spaces in the end. And then you go on with the latent spaces, and then you do the predictions from there. So quite simple actually. Helen?
To clarify when you're predicting the stellar mass, did you say that the early or more recent history was more important?
They're more recent. And so this is also, of course, also implies that when I'm saying that we can infer the assembly histories of different galaxies, the only thing I have to go off is the fact that I'm good at inferring stuff like star formation rates, stellar masses. I have only shown stellar masses here for the sake of simplicity. We test this on a wide range of different simulation outputs. So whole gas masses, gas phase modalities, black hole masses, star formation rates, you name it. But all these things are by their very nature mostly dominated by the recent assembly history. And so I will only make strong statements about the recent assembly history.
And for the graphs, what properties are you?
Everything.
Okay.
The only distinction is that when we're doing the kind of the cross-modal checks of looking at the environments versus the assembly histories, we take out everything that could be related to environment, like tidal forces, out of the merger trees, and vice versa for the environments, like anything that is directly related to the merger history, we take out, so that we can get a nice clean separation of.
So in that case, do you still need to be concerned about certain features that might not be well defined for earlier?
You do, but usually what you can do here is usually those things can be marginalized out just by the fact that they tend to be the noise in a given quantity is just so correlated with just exactly how many particles, what is the mass of a given halo. So it's pretty easy, I think, for whatever algorithm you're dealing with to learn that when you get below a certain limit, this thing here is no longer reliable. Don't pay attention to it, right? That's part of the nice thing about you are still when you're doing these things, even though you're just using a convolutional layer, you still have a message that's sent based on your current properties. And I think that if this thing encounters something, I actually know because I did a lot of trainability work on this. I know that when you encounter like a small halo in the early universe, the algorithm essentially just discards it, says this doesn't matter. Almost no matter what.
I have time for one more, anyone? Other than mine, if not, fine. Just,
Yeah. So I saw you compared to MLPs a couple of times.
Yeah.
I was wondering if you tried scaling the MLPs to see if it improves, if you fed it more data, because they've got very low inductive bias. So I was wondering if the GNNs are outperforming them just because you've injected the inductive bias in them, or is there a fundamental limitation to the MLP?
It is fundamental. It's a fundamental limitation to the MLP. Like what we get, we tried scaling up and down. We did the full sweep of everything we did with the GNNs. And what we ended up doing was to say we're just going to use every time we have an MLP, it's going to have as many parameters as our GNNs, no matter what. To say like, yes, it's a simpler architecture, but it's going to get a shit ton of parameters.
Yeah.
So we have these like 800,000 parameter MLPs to do, like 60 parameters to 6 mapping, which is maybe a little overkill.
Yeah.
But essentially, they just end up bottoming out on the performance around that, and that's consistent with what other people like. What we find is very consistent with what everybody else who tries to just smack MLPs on the problem of mapping from halos to Gauss properties find. So we find something that's very
Even if you feed them more data than the GNN.
you would. So okay, we actually did this test. You can if you take 100% of the training data and give it to the MLP. That compares to essentially using about 8% of the training data for the GNN.
Okay.
So of course you can beat this down, but I think that we essentially bottom out at like. I'm not going to say you can't make this better by just having a lot more data, but it's gonna be tough. It's gonna be tough. It's gonna be tough.
Yeah.
You're gonna have to burn down the Amazon to make that data.
Yeah.
thanks. Any questions online, George? No? Okay. Good, okay, then I guess that's it. If you do have more questions for Christian, as he mentioned, he's in the 412.
B412, yeah.
So that's over there, 4th floor, and he's here until tomorrow afternoon.
Tomorrow afternoon, yeah. I have different meetings with people already tomorrow afternoon, so I'm guaranteed to stay.
Otherwise, see you next week. Thank you very much. Let's thank him again.